Recording. It's recording now. Now, can everyone confirm whether you can see my screen, like the lecture slides? Okay, perfect. Thank you so much, Matthew and Stefan, for confirming. Okay, so welcome to CE305, Languages and Compilers, or as I also like to call it, the module on how to build your own compiler. Now, today we will be going through a topic called semantics or semantic analysis. Now, so we will be covering the first part of semantic analysis. That being said, before we proceed, in lecture 1, 2, and also in the previous all the lectures, we have already gone through the overview of different parts of the compiler. As you all remember that traditionally compiler has two parts, front end and back end. Now in the front end part, if you can recall that when lexical analysis happen, so the lexer takes in the input, generates the tokens, and then the tokens are processed by the parser, which is the parsing phase of the front end. And the parser generates the AST, or abstract syntax tree. Now, can someone tell me what is the next stage or the next phase of the front end of compiler? Let's say how many people has remembered? Yes, optimization, but optimization comes next. Next, not this phase, but next to next. So what happens before optimization happens? AST is one form of intermediate representation, right? But AST is processed by another phase. No, DFA construction actually happens before parsing. So technically during the parsing, DFA happens so that the parse tree can be generated, right? But what happens after you get the parse tree from the parsing phase, or the parser produces the parse tree? So what happens to the parse tree before optimization happens? It's technically right now in front of your screen on the lecture slide. Yes, Matthew, correct. So semantic analysis happen. That's why today's lecture will be focused on semantic analysis. So let's look at what it actually does. So we have considered tokenization and parsing. Both are, let me minimize this, sorry. Yeah. So both are steps to producing a compiled output, and both can be used to detect errors. Now, the next step is static semantic analysis. So the aim of static semantic analysis is to add additional contextual dependent information to the parse tree. What does that mean? That the parse tree is the hierarchical representation between the different tokens and the relationship between them. But tokens have additional information that defines what the token is capable of doing. So those are called contextual dependent information. So static semantic analysis is to add that type of contextual dependent information to the parse tree itself. And this is required to produce the appropriate compiler output and detect certain kind of semantic errors that your program might have. So did everyone understand that why we need static semantic analysis or semantic analysis? Can you post on chat, please? Although we will be going through the further details on each of this, but the overview is the purpose of static semantic analysis is to add additional contextual information to the parse tree that is generated from the parser. Everyone understood so far? Awesome. Thank you so much for confirming, Stefan. Okay, so let's look at context dependence or context dependency. So programs that are correct with respect to the language, lexical and context-free syntactical rules may still contain other type of syntactical errors. Lexical analysis or tokenization and conventional context-free syntax analysis or parsing are not powerful enough to ensure the correct usage of variables, objects, functions, statements, etc. So that's where other type of syntactic errors need to be determined. Now, before we move on, we have someone post something in the chat. So Matthew mentions it's looking for pieces of code that are technically correct according to the grammar, but don't make much sense. Yes, don't make much sense in purpose of execution. Now we will show you in the lecture with example, what does that mean? Although grammar might be able to tokenize and parse something as part of your program, but let's say when you execute, it doesn't make sense or it doesn't generate the desired output. So that's the type of syntactic error which is determined in the semantic analysis phase. Let me close the chat. Okay, so when we speak of compilers, so those aspects of the interpretation that require an analysis of the execution context are often known as the semantic analysis. Now, this is not the conventional definition of semantics in general, so keep that in mind, because some texts can also claim that such semantic analysis requires something more powerful than context-free grammar. But again, for the sake of theory, we will consider this as the definition of semantic analysis. So let's take this example. What parsing can check and what parsing cannot check. Let's say your input program, right? The input string that your lexer and parser processes is int a, where a equals 1. So here, let's say you have you are declaring that there's a variable a which is integer and the value 1 is assigned to it. So this to a parser or parsing phase is exactly same if you would have given it int b and a equal 1. So you are instead saying that have an integer like variable b, which is an integer, and assign 1 to a. But you can see that we actually haven't initialized a yet. So technically, the parser is not able to recognize this type of error. So when it comes to semantic analysis, that's the place where we are able to determine whether a variable has already been initialized as with a specific type or not, and then assigned a value. So other things can be, let's say you have int a, like you have declared a variable a as integer, but you are assigning the value 1.0 to the a, right? Now, we all know that 1.0 is actually a float. In practical sense, some programs do allow this to happen because technically you can convert float to integer, which happens as part of the program or the language defined. But some programs can also, some languages can also throw errors because of type mismatch. Now, I don't remember like if you have come across, but I have yesterday in the lab, someone actually came with this issue that when they defined their grammar, uh, they weren't like, they coded in such a way that their float in the grammar weren't able to convert to integer type. And that is actually being checked by the semantic analysis phase. So henceforth, as we can say that these type of issues can be checked using semantic analysis in the language. And that's why we need to learn this as part of the languages and compiler module. So the goals of semantic analysis is that it ensures that the program satisfies a set of additional rules regarding the usage of the programming constructs, such as variables, objects, expressions, and statements, etc. Let's take a few examples of semantic rules that we need to consider. Those can be variables must be declared before being used. Or we also need to keep in mind that a variable should not be declared multiple times in the same scope. Or another example of semantic rule can be that in an assignment statement, the variable and the assigned expression must have the same type. Another example also could be the condition of an if statement must have the type Boolean. Now, keep in mind that these examples of semantic rules are not exhaustive. These are only some of the most popular semantic rules that we should keep in mind, especially as a software engineer, if you end up designing your own language, not just as part of this module, but in the industry, if you end up developing a language as part of the team you're working for. So these are some of the common examples, but it can have other examples as well of errors or semantic rules that you need to keep in mind. Now, that being said, some of the categories, popular categories of semantic rule consist of semantic rules regarding types and semantic rules regarding scopes. Now, we will be going through each of these shortly. So let's take an example that when I mention that semantic rules regarding type, what does that mean? So type information classifies a program's construct such as variables, statements, expressions, and functions into different categories and imposes rules on their usage in terms of those categories with the goal of avoiding any runtime errors. Now, try to take what I have mentioned and try to realize what it is, right? Let's take the example. So you have the code, let's say your code or input program consists of int a plus 1 equal to a equal 1.0, and int power, this is like we are defining a function called pow with the arguments int n and int m. So that's your example input program. Now, when it comes to semantic rule of type information, what happens in this phase that based on each of the line of the code, we provide a category to it. For example, int a, technically a is the category of variable. And we also assign the type. So as you know that a here is a variable and it has a type of integer. Now in the second line of code, which is a plus 1 equal to, technically this is an expression. So this is the category of expression. And because we are trying to determine that a plus 1, whether it is equal to 2 or not, the type of this type of expression is Boolean. Same goes when we are assigning 1.0 to the a, this is a statement category. And because we are just doing an assignment and nothing more, so technically it returns void. That's why it has a type void. And in this line of code where we have int pow, which is pow is the function, and the passed argument or the parameters are int n and int m. So technically the type is that int, like the input values or the input variables are of type integer, and the return type is also of integer. So what happens as part of the type information here, we add more information such as category and type, which goes or accommodates the input code or the input program. So you need type checking to validate the rules itself. So we have seen the example. Now, based on the example, what type checking is doing is that it's validating the set of type rules. For example, the type of the variable must match the type from its declaration. Other example can also include that the operands of the arithmetic expressions such as addition, multiplication, subtraction, and division must also have integer types or floating types, and the result also has to be either integer type or floating type depending on the type of the variable. So if it is integer type and arithmetic operation is performed, then the return type should also be integer. Or on contrary, if it is a float, after performing arithmetic operations, the return type should also be a float. Other example of type checking can also include that the operands of the comparison expression such as equal, equal, or not equal must have integer or string type, but the result type is actually the Boolean type. So these are all part of type checking. Let's take a few more examples of type checking. For example, for each assignment statement, the type of the updated variable must match the type of the expression being assigned. Another example could be for each call statement. For example, here we have the function foo with the passed argument as v1, v2 till vn. So here the type of each actual argument vi must match the type of the corresponding formal parameter f or the function from the declaration of the function foo. Another example of type checking can be the type of the return value must match the return type from the declaration of the function itself. Okay, so is it clear what is type checking and like what it helps you to do so far? Okay, thank you so much for confirming, Dragos. So now remember that the parser or the process of parsing generates the AST or the abstract syntax tree, right? Now, in the semantic analysis, we add additional contextual information to the AST itself. So what happens, let's say the input for static semantic analysis is the AST, and the output is an annotated tree which consists of identifiers decorated with declarations and other expressions with type information. So that's what technically happens in the static semantic analysis. Let's take an example. If you have the input, which is a equals 5 plus a. So that's the expression as the input, right? So it generates the token as a equal 5, add or plus, and a. These are all the token, right? Then it goes through parsing, and the parser generates the AST. So the AST will look something like A connected to the assignment or equal sign. Assignment or equal sign is connected to addition sign, and addition sign is connected to 5 and A. So the AST will look something like this. But when you pass that AST to the static semantic analysis, then we add additional information about the type, which is given like by the example here, where we are saying that the A integer, because it's a type integer, we also add the information integer to it. Assignment, technically, it doesn't have the type, so it's a void type that we add to it. Same, when you do an addition, technically, the output type is an integer. So as you can see, we are adding more information about the type to the AST, and this is the theoretical representation of the output of static semantic analysis. Now, that being said, in practical sense, it's not this easy. So we will very soon, like shortly see in the lecture, that in reality, it's usually a bit more involved than what's shown here in front of the like as an output. But for theoretical purposes, let's call this as the output from the static semantic analysis. Now, normally the annotations are actually kept in a separate data structure, not as part of the AST. And things are also complicated because of the issue of scope, because depending on the scope, the type of variable can also differ as well. Now, for that, we will be shortly looking into other like mechanism or approach that we can take into consideration. But that being said, so the AST is the output of the parser or the parsing. And then in the static semantic analysis, we add the type information, which is stored in a separate data structure as part of the AST. Now, as I've mentioned, that the type information are stored in a separate data structure, that is technically called the symbol table. So semantics checks refer to the properties of identifiers in the program, which consist of their scope or type. Now, you need an environment to store the information about the identifiers, and that is done through a symbol table. Each entry in the symbol table consists of the name of the identifier, and it also consists of additional information such as its kind or its type, or whether it's constant or not, and so on. So this is an example of the symbol table where, let's say, you have the name, which is foo. We know that it is a kind of a function. And the return type, it could be something like you pass the argument int, 2 integers, and the return type might be Boolean instead. So as you can see here, so these are some of the other examples of like you can have parameters such as m and n, which are parameters or arguments, and they are of type integer. You might also have a TMP or temporary variable, which is a variable, but that one has a type Boolean. So given this example, you can see the symbol table can be represented like this. Now we have someone post something in the chat. Let's see. So Matthew is saying, I was thinking about this, would something like a stack of symbol tables work with regards to scope? I mean, how you implement in practical sense, that could vary, but absolutely you can actually use stack of symbol tables to understand the scope. So in the stack, if we do, let's say, like first in first out in a way, where the first variable that is stored, if you implement the symbol table as a stack, So the one that comes first, you are determining that that has a higher precedence in the scope, then absolutely you can implement in that way. Now, that being said, Matthew, oftentimes modern programming languages can be very complex as well, right? Now, the scope can have different hierarchy, which we will be actually seeing with example later today only. But just using a stack might not be sufficient in that scenario. So you might use multiple stack to generate that hierarchy, but that is only in the practical sense, right? Right now, we are just exploring the theory behind the concept. Does that make sense, Matthew? Perfect. Thank you so much for confirming. Okay. So as I have mentioned here, let's say if we are implementing the symbol table to add additional information about the type, as you can see from here, it doesn't tell you much about the scope. So that's why it's very complicated to determine the scope just from the symbol table. Now, since I mentioned about the scope, let's talk about what is scope information. Scope information characterizes the declaration of identifiers and the portion of the program where use of each identifier is allowed. For example, you can have variables, functions, objects, and labels within the whole program, but how to know that where each of these identifiers, such as variable, functions, objects, and labels, are allowed to be executed or to be defined, right? That's why scope information is very important. Now, lexical scope is a textual region in the program which could include statement block, for a formal argument list, object body, function or method body, module body, or the whole program itself consisting of multiple nodes. So technically, lexical scope is the textual region in the whole program, which can consist of different parts, as I've already mentioned. Now, that being said, the scope of the identifier uh, is the lexical scope in which it is valid. So let's take an example here, right? So you have a C program, which might have the lines of code, something like you have open bracket or left bracket, int a, you're initializing the variable a. Then you might have few more statements in between, and then you're opening bracket again, and you're initializing a variable b. Now, before you initialize the variable b, keep in mind that since you on top, you have declared the variable int a. So the scope of a belongs in till this part because it is already defined. Now, after you have defined the int b, because you have declared the variable b with the type int here, here the scope of b is also added along with the scope of a. And it goes on till, because we close bracket here, so int b or the variable b will only be operatable within this scope, which is like shown using the mouse here. But after that, only scope of a can be like determined. So b doesn't fall within the scope after this bracket. So in C, the scope of the file static variable is actually within the current file that it like looks into. The scope of external variables are actually through the whole program itself. And the scope of automatic variables or formal parameters and function static variables are actually part of the functions to which or in which they are declared and used. So this is how like scope is determined in the language C. Now, scope of, let's say, of formal arguments of functions or method can be determined like this. Let's say you have the function called factorial, which has the passing argument as n, which is a type of integer, and the factorial also returns the type integer as well. Now, based on this, what is the scope of the formal parameter of n? If someone asks you that, right? Now, here, given this example of factorial function, the scope of n is actually within this function only and not outside this function, because n is only used or declared and used within the function. So that's the scope of n in this function itself. Or if it's a part of the larger program, it's still the scope of n will be limited to this function. Now, let's look into scope of labels. So let's say you have here a function which has a return type of void, and the function is f. So inside the function, you are saying that go to L, which is a label. Now, here, at a later stage, inside the function, you are defining that L is the label. It continues the statement that a equal 1, and then again you might have few more statement in between and go to L, right? So what if now I ask you the scope of the label L, right? In this scenario, the scope of the label L is actually the lines between where L is defined. So you are defining the label L here, and then making this or declaring the statement under the label L. So the scope of label L is only within those lines within the function f. We have someone post something in the chat. Okay, pretty sure labels in C are global scope. At least I seem to remember that they used to be. It depends on how you are defining the label. So not all labels are global, Matthew. You can also have labels within the function. If the labels are within the function, then it will only be limited within this that scope or portion of that particular function. Does that make sense, Matthew? Yeah. So again, it depends on how the program is written as well. That's why we will be going through a few more examples to see. Like, it's very important when you define a language to understand that, like, to follow some of the convention that helps you to avoid any form of ambiguity or, let's say, differences or issues that you might get, especially because of differences in scope. So as a programmer, it's your duty to keep these things in mind, that how scope works for different variables. So here, let's take this example, right? So we have the scope of object fields and method. Let's say you have a class, you define a class called A, where you are saying that the A has the variable which is X of type integer, and A also has a method which is G, which has a return type of void. And within the G, you use X, right? By defining X equal 1. So that's your class A. Now you have another class called B, which inherits from A. Now inside the class B, you define the another function, which is you call it h with the return type int, and inside the h you are using g, right? Now, given this example of two classes where one is inheriting the other one, so what do you think the scope of the field X and what is the scope of the method G is? Can someone specify that in the chat? So given the example in front of you, what do you think is the scope of the field or like variable X, and what is the scope of the method G given the two classes? So Matthew, again, you do not have to think whether it's a private class or a public class. That is not given in front of us right now, right? So let's think that these both are public in a way, right? So given you only have two classes, A and B, where B inherits from A, what do you think is the scope of X and G in this purpose, in this case? Yes, it is both classes because B extends or inherits from A, right? And B also has the a method, which is H, which uses the function G. Now, G itself, as you can see here, G itself uses the variable X, right? So both the classes are actually using like X and G fall within the scope of both the classes in this scenario. So Matthew, you're correct. Okay, so let's look into semantic rules for scope. But before we move on to this, learn more about semantic rules for scope, let's take a 5-minute break and we will resume after the 5 minutes. Is that fine with everyone? How's everyone doing? Why only today Matthew is the only person interacting with me? Is everyone fine? Is everyone there? Okay, thank you so much for confirming, Stefan. Okay, so let's take a 5-minute break and we will resume shortly. Matthew, I actually love it. Like when people interact, I really like it. If you're feeling chatty, it's even better, right? But I also want everyone, not just Matthew, which is great that Matthew is engaging and interacting, but I also want others as well. So that at least I know that other people are also in the lecture, right? Okay, Curtis, yeah. The lecture will be available also like as a recording on Moodle. So in case if you have missed anything, you can also follow back as well, right? Okay, cool. 5 minutes break and we will resume in 5 minutes, okay? Let me pause the recording. And it's recording again. Perfect. So let's look into the semantic rules for scope. So the main rules that you need to keep in mind regarding scope is that rule number 1 is use an identifier only if defined in the enclosing scope. And rule number 2 is do not declare identifiers of the same kind with identical names more than once in the same scope. So as a developer of the language, you need to keep these two rules in mind when it comes to scope. Now, you can declare identifiers with the same name with identical or overlapping lexical scope if they are of different kind. So that is perfectly allowed. Now, since I've mentioned these two rules, let's take an example, right? So an example can be that you're declaring a class X, where inside the class X, you're declaring variable with int X, and you're also defining the method inside the class X as X as well. And it takes the argument, which is of X. So you are saying this is not a good way of writing a code, because they're like the type information could be like mismatching, and errors can happen because of that, right? So you definitely want to avoid this type of coding when it comes to like developing your program, and developing your language. So you should have some form of error checking to see if these the names are not this of the same, or else uh, like your program should like throw the error back to the programmer. So now the question is when to perform static checking, right? A more structured approach is to separate out the distinct phases of the compiler itself. We can think about performing semantic checks only after the AST has been built, not while it is changing. So what that means, that when your parser, after the parser has generated the AST, then only you perform semantic checks, not while the parser is producing the AST. Because AST, let's say, depending on your input program that you are passing to the compiler, so your input might change in between program, right? Uh, so semantic analysis or semantic checks shouldn't be done while your input is being changed. Only after your input goes through the parser and the AST is generated, then only after you have the complete AST, you perform semantic checks. So this approach is more flexible and less prone to errors. Now, arguably, for a compiler, it is better to concentrate on reliability and correctness than on efficiency, especially given the performance of modern computers, which are capable of computing more efficiently in general anyway. So let's explore static and dynamic properties. Now, when I say static or dynamic properties, let's first look into static properties, right? Static properties are those properties that can be determined by examining the text of the program without actually executing it. So here you are checking the static type of the variables of the input program. And why it's called static, it's because you don't even have to execute it to understand whether the type matches or not. So an example here can be, let's say you have these two lines of code where x equals x plus z and z equals x plus 2, right? Now here, we know that all uses of x on the right-hand side refer to the same variable, x itself. And the value of the second reference to x is determined by the first assignment statement or the first line of code, which is this one. Now, the final value of z depends on the initial value of x and itself. So henceforth, here, if you are given these two lines of code, you can examine the program without even have to execute it. And you will know that these two line of code will execute without any issue. So there won't be any semantic error if you have these two line of code. And because you didn't have to execute it to understand whether an error might happen or not, like semantic error. So this type is called static property or static semantic analysis. Now, in contrary, you might also have dynamic properties. The dynamic properties are those that can only be determined by considering all the possible executions of the program. Now, that being said, what do I mean by that, right? Let's take this example. Let's say your input code is x equals x divided by z and x equal y minus 2. If we have these two lines of code, first of all, in the first line of code, especially if it's a division, what if the z is 0, right? So no matter what is the value of x here, if it is divided by 0, it will like give you an error, right? So depending on the value of z, it can throw an error. Same, if we have this where x equals y minus 2. So here, if x is less than 2, then and z is equal 10. So technically, given these values, the value of z in x equals x divided by z would be very different, right? So what we are doing, that if your code do consist of similar lines of code here, especially consisting of division operation, then you have to consider all the possible executions of this input program code to be able to determine whether an error, semantic error might happen or not. And this type is called the dynamic property. So in general, dynamic properties are not computable till execution. Sometime, let's say now, if we have to understand the differences between dynamic versus static type checking. So sometimes the differences or the border between dynamic and static type checking is a bit vague. For example, let's say if you are given the code or the input line, which is x equal 1e minus 2. Technically, 1e minus 2 means 10 to the power minus 2, right? Which is 0.0001. That's the value of 1e minus 2, right? So here, we might be able to deduce statically or even dynamically that the type of x is actually a float, right? So this is one of the example where you can see you can determine either statically or dynamically that the type of x itself is a float. Now, before we continue, we have someone post something in chat. So Matthew mentioned, sorry, I'm a little bit confused about how the division makes that particular case a dynamic one. Okay, Matthew, good point. Okay, going back here, right? Let's say here, how would you know whether an error would happen or not? Let's say it doesn't matter whether you are doing static or dynamic type checking, right? Let's consider if you have the this code x equals x divided by z, right? Let's say z is 1 and x is 2. So 2 divided by 1, technically it's 2, right? So the value of x becomes, the type of x becomes integer in this case, or float. Either way you can use, right? But what if the value of z was 0? So then 2 divided by 0, what is it? Usually a lot of programs throws error, when you execute it, right? So even if 2 divided by 0 is a possible, let's say, what do you call it? Mathematically or like theoretically, mathematically, it's possible, but technically anything divided by 0 is like infinity in a way, right? So if your program didn't know the value of z itself, so until execution, you won't be able to determine the type of x, like based on this x divided by z, right? So why this is called dynamic type checking is because you have to wait till the execution and consider all the possibilities of the different value of x and z to be able to understand whether there will be an error or not. That is the main difference. If you had, so in static, say if you do plus or minus, right? Doesn't matter what you do plus or minus with, usually the return type or the type of the variable still remains the same. It's only when it comes to division, you have to consider all the values of, let's say z in this case, to be able to determine whether the value of x, like the type of x, will throw an error or not. So Matthew, you are asking, I assume this is only true if we can't see where z is initialized. Yes, that is correct. So if we actually do not know the value of z, right? And you also see, when as human being we see this, we are able to determine like the value of z more easily. But when you implement or design a language where your program supports, let's say, different type of variables and different assignment, then oftentimes the execution could be difficult. So that's why dynamic type checking can happen during the execution time. So, okay, Matthew has mentioned otherwise we would be likely to determine it all during compile time. Yes, unless its initialization is based on an external file or other user input. Yes, Matthew, you are absolutely right. So I hope now you got the idea. So static type checking will be something where it's easily determinable that whether the types are matching or not, or whether there will be an error or not. Comparatively, the dynamic type checking will be actually where you have to consider all the possibilities of the execution of the code, and then only you can determine whether a type error or any form of other errors, semantic error, will happen or not. That's the only difference between like dynamic and static type checking. Matthew, is it understandable now? Okay, thank you so much for confirming. So as I've mentioned, like oftentimes in practical sense, there can be like very vague or like little differences between the dynamic and static type checking itself. So in some cases, we can conservatively deduce apparently like dynamic properties using static techniques as well. Uh, One such example is symbolic execution, where symbolic execution is a means of analyzing a program to determine what inputs causes each part of the program to execute. So as I've mentioned earlier here, so as you can see, like until unless we know the value of z, like it makes it difficult for us to consider whether there will be an error in this line of code or not for x, right? But if we are using symbolic execution, where like the input is known, and based on the input, we know that each part of the program is able to execute, then we are technically like deducing dynamic properties using static techniques itself. So keep this in mind. Okay, so what are the tasks for semantic analyzer, right? So the task for semantic analyzer consists of find the declaration that defines each identifier instance, determine the static type of the expressions, then perform reorganization of the abstract syntax tree that were inconvenient in parser or required semantic information. And finally, detect errors and fix them to allow further processing. So these are the definitive tasks for the semantic analyzer. Now, typical semantic errors consist of, let's say, you have multiple declaration, which is where a variable should be declared in the same region at most only once. Or you can also have undeclared variable, where a variable should not be used without being declared. You can also have type mismatching, which you might have already experienced while you were coding in Java, which is where an example could be that the type of left-hand side of an assignment should match the type of the right-hand side of the assignment. Other typical semantic error can also consist of, let's say, wrong arguments, where method should be called with the right number and the type of the arguments. Another example can be definite assignment check, especially in Java, where conservative check that simple variables are assigned before they are being used, right? So these are some of the typical semantic errors that your language should support. There could be much more, but these are some only examples to give you an idea that when you are designing your language, what you should keep in mind, especially as part of semantic analysis. Okay. So today's lecture was anyhow the first part of the semantic analysis. We will be continuing with this again in next lecture. But that being said, any question so far? Any question? Okay, thank you so much, Matthew, for confirming. Thank you so much, Curtis. Thank you, Sokanya. Okay, cool. I will be posting this lecture shortly on Moodle under Unit 7, so you can revisit the lecture at any point. But let me stop the recording.